In this lecture we're going to talk about the normal approximation to the binomial distribution. Alright, so far let's review the ways in which we've looked at the binomial distribution. Many different ways at this point. First, we've done it from first principles, we'll just say from scratch, and we did that with the probability at the end of probability theory in the second module. We then looked at the binomial formula, tables. We had to learn how to use the cumulative distribution. We've done the Poisson approximation. Right, remember we had two conditions, that n is large, and you start thinking about it at 50, and essentially p is small, but we did it so that the mean of the distribution, which is np for the binomial, is less or equal to 7. Alright, and this guarantees essentially that p is small. Alright, and today in this lecture we're going to do the fifth way, and that's the normal approximation. And this method and what's happening here to the binomial distribution happens with many other probability distributions, that is, that they could be approximated under certain circumstances to the normal distribution. For instance, the binomial is a particular distribution which is useful to us, but it has two different outcomes on one trial, right? Like a probability of head, a probability of tail. You can imagine a distribution for the roll of the dice where you have 6 alternatives on one trial. Alright, and so when you're doing 2 trials, you've got a whole bunch of different combinations, right? Instead of 4 different possibilities, as with a coin toss, head head, head tail, tail head, head tail tail, that type of thing. On the roll of the dice with 6 alternatives each time, you get a heck of a lot more different possibilities, 36 of them on 2 rolls, etc. In other words, there are distributions like the binomial, but much larger, more complicated. And those are called multinomial distributions, and they also can be approximated with the normal. And that's a sort of a lead-in to the next module, where we talk about what are called sampling distributions. But in any case, back to our normal approximation. We have two conditions that we'll use: n greater than or equal to 50. Alright, and secondly, that the mean, which is np as above, is greater than or equal to 5. Alright, for some of you that first condition will be very important, especially if you're doing your own research and you're wondering what sort of sample size I should take when I'm dealing with proportions. At least 50. Okay, below that things get a little shaky, but we'll look at that in a second. Let's look first at a web page that shows you this. It's actually called the central limit theorem, which is in the next module. But in the diagram here, you'll see what we're doing essentially when we're approximating a discrete distribution, the binomial, with a continuous distribution, the normal. Okay, so you can see the blue bars here, not really bars, but boxes for the histogram, right, as in the first module, and we create these little boxes around each number. Alright, you'll see down here, for instance, the number 8, and around the number 8 you'll see this little bar, and that bar goes down a half a unit to 7.5 and up half a unit to 8.5, and it has a certain height to make a probability, and each one of the outcomes Right, I have little n of 20 here on the binomial probability of a half. This is from somebody else's website. And so we have outcomes going from 0 all the way through 20. Okay, so that's 16, 17, 18, 19, 20, and it stops there somewhere. Okay, but you'll see at the boundaries it essentially goes to 0, just like the normal distribution. The normal distribution goes off to infinity. But in any case, so we have these little bars to create widths around each of the numbers, and these boxes, approximate the normal distribution, which is drawn on top. Okay, so let's go back here, and so we have, and I'll do this crudely, a normal distribution, and at some point, right, as in the example that I had, the number 8 will go up a half and down a half, 7.5 to 8.5. We do that so the next number, say 9, goes from 8.5 to 9.5 in any case. Alright, so we draw this box. Okay, and so we're going to say that the area under the normal distribution approximates the area in the box. And that'll be true as long as this little triangle here, which is more than the box contains, is approximately equal to this little triangle here, which is not included with the normal, but it is included with the binomial. Alright, so we expect these two little things to average out in the long run. Alright, so that's how it's done, and of course I'm drawing it to a huge scale here so that you can see it, but when you have n of 50 and p equal to a half, you start having a lot of these little boxes and they sort of become very tiny. Okay, so let's look at an example.